recording, and let us continue the introduction to the course and the course material that we will cover, inshallah. We discussed the evolutionary computations and also neural network and fuzzy logic. And as we mentioned, you can use two or the three techniques, and you can hybridize them together, so you can have the benefit of both techniques, neural network and fuzzy logic, for example, and you can avoid the shortcomings of each technique. So you can come up with the hybrid technique, and usually this would be the case. You have the three major techniques that we will cover here: neural network, genetic algorithm. طبعا genetic algorithm is not we will not limit ourselves to genetic algorithm. We can replace it by any other technique, such as particle swarm or differential evolution or whatever here. But evolutionary computation, let us say, in this circle represent the evolutionary computation technique, okay, whether it is GA or others. So you can use GA with the neural network to optimize the weights. So you can have an overlap here or the intersection here. You can use fuzzy logic with the neural network to fuzzify each input of the neural network. You can fuzzify it, you can convert it to linguistic values, and then you can process. This is what we call neurofuzzy technique. You can use also genetic algorithm and fuzzy logic together. So the optimization technique here will shape the membership functions of the fuzzy logic, and also it will affect the output. It can optimize the output if you use the genotype. So we will discuss this in details later on. Or you can hybridize all the three techniques together. You can use fuzzy, neuro, and use genetic algorithm to optimize the parameters there. So you can hybridize each two techniques together, and this hopefully will give you a better technique which combines the advantages of both and avoids the shortcomings of these techniques. So this is just an example of the neurofuzzy. You have here the inputs of the neural network. This is called the ANFIS, Adaptive Neurofuzzy Inference System. This is well-known name for the neurofuzzy hybrid system. You have here two inputs, X1 and X2, and each input you fuzzify it. You have here two fuzzy sets, B1 and B2, and A1 and A2 for X1, and then you can proceed with the multiplication here and addition weights of the neural network here, and of course you can continue. We will see the structure of this, but this is just an illustrative example for the neurofuzzy hybrid system. The application of the artificial intelligence, of course, it becomes very popular nowadays, and to have the several applications of the neural network. In terms of control, let us see the intelligent control versus classical control. So if you see the comparison here in terms of the basic concept of the classical control is model dependent. You have to model your system in a set of differential equations to characterize the performance of your process, of your plant, of your system. So you have to develop the model, and then you can do linearization, and you can get the eigenvalues and so on, and you can design the controller or whatever you need. So you need a model dependent. But here for intelligent control, and this is the major advantage, it's a model free. We don't need the mathematical model of the exact mathematical model of the plant. So it is a model free. You don't need to develop the model. It handles input-output description or try to establish a relationship between the input and the output, whatever the components of your plant or of your process. Characteristic of the classical control also need to know prior information about the system dynamics. As you mentioned, you have to develop the model suitable for the system that can be easily modeled. If you can model the system, so you can develop the model and you can go through this. However, doesn't need here for the intelligent control, doesn't need to know all about the system dynamics and the conditions appropriate for complex systems where you have a lot of uncertainties and the complexity that is complex to be exactly model exactly. Examples of the methods we have here: open loop system, closed loop system, and system modeling, and so on. Here you have the techniques of the intelligent control, fuzzy logic control, neural network, and genetic algorithm, and swarm intelligence, and so on. So this is in terms of control. Of course, you have a lot of different areas where you can find artificial intelligence take place there. Autonomous planning and scheduling of tasks aboard spacecraft, aboard the spacecraft, aboard, I don't know what it is. Tasks aboard a spacecraft, beating Gary Kasparov in a chess match. You can have gaming, artificial intelligence in gaming, and also steering a driverless car. This is another application, is understanding language, and you have in your mobile Siri or whatever, so it can have some kind of intelligence. Robotic assistance in surgery, and monitoring trade in the stock market to see if insider trading is going on. You have it movies, autonomous rovers to explore harsh environment in military application. You have in games, you have in industry, and you have it in recognition of face recognition, robotics, appliances. You have some also fuzzy logic controller there implemented in cameras and implemented also in washing machines. You have it also in transportation, as you mentioned, the driverless cars. You can have also the intelligent control or intelligent artificial intelligence applications in medicine or medical area. You have also in economics and the finance, and this is usually the fields where you can find artificial intelligence applications. Al-Hassan Ali, you have a question, Al-Hassan?
Yes, Doc. My question is the power plant DCS be considered an artificial intelligence?
Your voice, Hassan, is not clear. Can you repeat your question and try to...
Do you hear me now, Doctor?
Now it's okay. I hope not you continue as such.
My question concerns the DCS system of such power plants. Would it consider be an artificial intelligence control of some type, or?
DCS, distributed control system.
Yes.
I don't think, unless you have some kind of intelligent controllers there. إنما usually if it is a BI controller or fixed, or adaptive حتى even gains or classical controllers, which I guess. So I don't think the artificial intelligence is there. Unless you have any, if you want to clarify something and help us in.
It's just the concept of mixing many hardware controllers. Some of them are PID, some of them are different. And then having the stages of integrating from one level of control to another and mixing even different controllers to all combine under the DCS.
The point is, if these controllers are intelligent controllers, and you can have some kind of neural network application or fuzzy logic or these evolutionary computation techniques, so it becomes intelligent controller. Otherwise, if you use classical controllers like BI to control the plant or the process, so it becomes a classical controller.
Okay. Okay, thank you, Doctor.
Okay, thanks.
Okay.
Yeah, Professor. Just regarding the DCS, because it's another alternative of the PLC, so it's already programmed with programmed commands for monitoring and control. So, as you mentioned, I don't think it's classified as one of the AIs. It's only belongs to the classical control methodology, I believe.
Yeah. So it is not able to, as we defined the intelligence and artificial intelligence, and the definition is you can analyze, you can take a decision, you can learn from experience, you can do this and that. So if you have such capability of the DCS, then we can say no, it is intelligent, which is I doubt.
Doctor.
If you allow me, Doctor, they actually have in the diagnostic system of the DCS, for example, if you have a faulty sensor or whatever, it will indicate the fault precisely, and it'll tell you how to fix this fault, which is kind of an intelligent in that sense.
Identification also based on some mathematical models. If you can identify the fault, and this is not necessarily to be intelligent way. And if you have any fault happens with some measurements of currents, voltages, pressure, temperature, or whatever, then you can identify the fault and you can allocate the fault. But this based also in some mathematical models. So yes, it is not an intelligent in this case.
Okay, I understand that. Thank you, Doctor.
Abdulaziz Khalid. Abdulaziz Khalid, Johnny.
Yes, Doctor.
Yes, please.
My question, if you can clarify on the when comparing intelligence control versus classical, we are saying intelligence control is model free, but my understanding from previous courses is that a neural network, for example, trained for a certain system cannot be applied on a different system.
Yeah, but it is a model free. You don't need the model. If you have a plant, look at the real life. And this is the plant. Assume that you don't have the plant model. This is the physical plant. This is the physical process. You have an inputs and you measure the outputs. And then you can train the neural network here. Okay? Even you don't need to have the model of the plant in order to train the neural network. Right?
Yes.
طبعا definitely when we are doing with the research topics, you are not having this plant physically. What you can do is, if you have the mathematical model, this is just for research. In real life, you can have the plant as it is, without knowing any dynamics inside, and you measure the inputs and the outputs, and then you can train the neural network here. Okay, but يعني for research and the development or so, you don't have the plant in order to try on the plant or do some experiments or so. So you can replace the plant with the mathematical model. Hopefully, the mathematical model reflects the dynamics of the plant يعني in accurate way. Okay.
Okay, thank you for clarifying.
Okay, thanks. Okay, some advantage of the artificial intelligence. It's more powerful and more useful computers, new and improved interfaces, solving new problems, better handling of information, and relieves information overload, conversion of information into knowledge. Yani this will be clarified more when we discuss in details such things. Increased costs, difficulty with software development, slow and expensive, and this is why we have Winter 1 and Winter 2. It needs high computation capabilities, but nowadays one of the enabling technology for the artificial intelligence to dominate these days, the computational capability now becomes stronger and stronger. So this will facilitate implementation of the artificial intelligence techniques. Few practical products have reached the market as yet. They're still in the process, but what I want from you guys, and as I asked you before, and we will work in groups, at most 3 students per group, and I would like each group to freshen up your industrial attachments or knowledge and list down industrial applications which use classical control in their company, and identify any application in the industries that has applied artificial intelligence in their system. And you can search for some of the industries they start implement. As we mentioned, you have different areas here for artificial intelligence applications. You can pick one area and try to find out an application of artificial intelligence, how they implement the artificial intelligence, and how the artificial intelligence replaces the classical control, what are the advantages they gain, and so on. So propose any one of the artificial intelligence methods for any appropriate system and industries. You can do this. Explain why did you choose the proposed technique. So this assignment I need it after probably 1 week from now. So next Monday, and coming Monday, inshallah, you can submit like 3 pages on this assignment. Okay, is it clear?
Okay.
Monday 31st. January becomes February. February 1st. Today is 25, so Monday, February 1st, I need 3 pages from each group addressing these points. Okay.
Doctor, how can we, be in a group? Are you gonna assign us with other colleagues since we do not know each other and it's not in a class course yet?
Well, yeah, I don't know. Of course, and I can move, but this also will be randomly. So if you know each other, this will help a lot. Maybe through the WhatsApp group, you can form the groups from there. I don't know. I don't know really. You can just put an announcement in WhatsApp group. If anybody needs to form a group, please. Of course, you can.
All right, I'll do. Thank you.
Okay. And if later, probably when you have some of you without any partner in the group, so we can combine you together as one group. And when we have 3 individuals, we can combine them. But I would like to give you an opportunity to, probably some of you know the others, so you can team up with you. This will help us in doing the work. Okay. So we give you a brief introduction in evolutionary computation, neural network, fuzzy logic, a description of each technique, difference between classical and this, and the application of the neural network, and this is the how. If you have any question, otherwise we will start the next topic, which gives you a brief introduction to optimization. As we discussed earlier, and we will start with the evolutionary computation, then fuzzy logic, then neural network. Evolutionary computation, we will give you the basic concept first with the evolutionary computation, and then we will discuss 3-4 specific techniques in this. But here we have, evolutionary computation can be implemented as a single objective optimization or multi-objective optimization. Multi-objective. Probably I will delay this multi-objective later on after having this fuzzy logic and neural network. Or at that time we can decide, and we can consult you and decide whether we continue to multi-objective. Multi-objective is a little bit different than single objective, and it is a different approach completely. So I would like here to give you a brief introduction to optimization, just to refresh your memory about the optimization techniques, and also the principle of optimization, problem formulation, what is the major component of the optimization problems to formulate it, the steps used to solve optimization problems, what are the steps, classification of optimization problems in terms of convex, non-convex, multimodal or unimodal optimization, and so on. So obstacles and difficulties in optimization we will discuss. Unimodal, multimodal functions, convex and concave, minimization and maximization. Some problems are minimization and some others are maximization. So how to convert from here to there. Necessary conditions for optimality, and solving unconstrained optimization and constrained optimization problems. I guess some of you already maybe may take some courses in optimization, so this part will be just to refresh their memory in this regard. A typical engineering problem, you have a process that can be represented by a mathematical model, and you also have a performance criteria. such as minimum cost. طبعا this is just an example. And if you have a control problem, this performance criteria could be the could be, for example, the settling time, could be the overshot or deviations, maximum deviation, could be the eigenvalues, whether it is in right-hand side or left-hand side, you need to push, and you can define a performance index to search for the controller parameters that move the eigenvalues to the left, or you can put it in whatever area in left you can have, and you can design your controller to set the eigenvalues of the closed loop system within this D shape. We call it D shape. So you can have a controller and you optimize its parameters to give you the eigenvalues in this shape. So you define this performance index, and then you can do this. Could be minimum cost, could be maximum profit, could be anything else. So you have to define the performance index. So you have the process, and you have to define the performance index. So the goal of optimization is to find the values of the variables, or optimized variables, in the process that yield the best value of the performance criteria. So you need to minimize something or maximize something. And there's two ingredients of an optimization problem, and two major components, which is the process with its, of course, constraints. And this process involves several constraints. So you need to minimize a performance index or maximize a performance index under these constraints. So what is the optimal variables that satisfy the constraints, no violation, and at the same time minimize or maximize the performance index? Okay, so this is the typical engineering or typical optimization problem. Some typical performance criteria or performance index or objective function or cost function. Sometimes we call it cost function. All are the same. Performance criteria, performance index, objective function, cost function, they are the same. You can maximize the profit. You can minimize the cost. You can minimize the effort. You can minimize the error, speed deviation, or whatever. Any measured variables, you need to minimize the error there. You need to minimize the losses, for example, in your plant. Best product quality, you have to maximize the quality of the product. The need to express the performance criteria in mathematical form. So you have to express your mathematical form and your performance index or performance criteria in mathematical form. So this is called the objective function, as you mentioned. If you have, for example, time, or for example, error, especially in control area, usually when you design a controller, BI controller, and you need to optimize how much KB and how much KI in order to minimize, for example, the integration over the time delta أو الإيرور سكوير بتصل الإيرور سكوير. الإيرور سكوير could be مثلا delta omega. If you have a motor and the speed deviation of the motor. For example, this is E square. And this is just one performance index that you can use. You can multiply this error by time, so you are incorporating here also the settling time with the overshot and undershots deviation, and this is the settling time if you incorporate the time here. This is just one example there. Okay, so if you have any question, please raise your hand. Okay, now we have a static optimization. If all the parameters are stationary or static, no variation with time, variables have mathematical values or numerical values fixed with respect to time. So for KB and KI, for that example of the controller, the KB is fixed, the KI is fixed. So this is the kind of static optimization. But if you have the variables also is function of time, so you optimize a variable over a time, and you instead of optimizing مثلا x, this is a numerical value, you optimize x of t. So this variable is changing with time, and at each time you are searching for the optimal values. So this is a kind of dynamic optimization. Variables are function of times. Every optimization problem contains three essential categories. At least one objective function to be optimized. You have to define the objective function. This is the major component, one of the major components in optimization problem formulation. You have to define your performance index, equality constraints, and inequality constraints. These are related to the operational constraints of your plant. This is operational. You have to satisfy all the operational constraints of your plant. So, for example, in your system, you have to have, if you, you can have, for example, in bar system, for example, just an example, you have here bar system or synchronous machine or motor or whatever. You have an operational constraints here. For example, for bar system, the voltage must be within certain bounds. V minimum, voltage minimum, and voltage maximum. So these are some kind of inequality constraints that must be satisfied. And also the equality constraints, let us say, in the input power, مثلا here will be input equal to the P output plus losses. And we have here B input equal to B output plus losses. So this some kind of equality constraints. And you will find for each plant some operational constraints. Some of them equality constraints, others are inequality constraints. So these are the three major components for the optimization problem formulation. Okay. What is the feasible region? What is the feasible region or feasible solution? Definitely, what is the feasible solution? If you find the solution here, you have to solve this problem and find the solution. This solution to be feasible, it should satisfy all these constraints. If you have a solution that satisfies all these constraints, but this is called a feasible solution. Otherwise, the solution is unfeasible. So let us see what is feasible region and feasible solutions. By a feasible solution, we mean a set of variables which satisfy categories 2 and 3. satisfy the constraints, equality and inequality. The region of feasible solutions is called the feasible region. Of course, we are, for solving the optimization problem, we are solving we are searching the feasible region, and we exclude all the unfeasible solutions. For example, if you have here some nonlinearity constraints, and this is the feasible area regarding this, and you have also another, nonlinear constraints and nonlinear inequality constraints, linear inequality constraint, linear inequality. So with this, x greater than x1 greater than 0, x2 is greater than or equal 0. So this is the one here. You have this is x1, so x1 must be equal to 0. So we are in this region, and the x2 also must be greater than 0. So we are here, and this constraints, you can see whether this is unfeasible region for this constraints, and this is feasible region of this constraints, and this is a feasible region of this constraints, and this is a feasible side of this constraints. So all these constraints, and this is linear also constraint. This is linear straight line. Here represented by a straight line, it is continued here. This is the equality constraints. Assuming that you have only two variables. So if you have two variables, and with the equation of two variables, x1 plus x2 or 2x2 should be, for example, equal to whatever, 5, and so on. So assume that this straight line is represented here. Okay, so that means if you have a straight line and this must be satisfied, the problem solution must satisfy this equation and must be a point on this line. But considering the other constraints, this becomes the feasible part of the nonlinear constraints, and this is the linear constraints. So in this case, this part of the line represents the feasible region, this part of the line. So each point here is a feasible solution up to this point. Okay, so this is the feasible region here. Here, if there is a solution here, this solution is unfeasible and it doesn't satisfy the linear constraints. Okay, if you have a point here on this line, it satisfies the linear constraints, but it doesn't satisfy, for example, this constraint, this nonlinear constraint. So this is unfeasible solution. This is unfeasible solution. So for this specific configuration, the feasible region are this part of the straight line, in which it satisfies the equality and inequality constraints. Is it clear?
Yes, it is clear.
Okay. Sharif Ibrahim. Sharif. Salam.
Doctor, what are the meaning of inequality constraints and equality constraints? Mathematically.
Here it is. When I say, مثلا, in one system, the input power equal to the B output plus losses. This must be satisfied, right? This constraint must be satisfied. يعني, am I right or not? يعني input equal to the output plus losses.
Yes.
This must be satisfied. And this constraints must be satisfied. This is an equality constraint. And equal, you have this here equality constraint. But when we say مثلا voltage must be within these bounds, so this is inequality constraint. V is greater than or equal, this is inequality constraint. V less than or equal V max, but this is inequality constraints. Okay? So this is the equality and this is inequality constraints. In this example, assume that x1 is greater than 0. Where is the region where you have x1 greater than 0? This is x1. And this side here, x1 is less than 0, right? Down here, x1 is less than 0. Am I right or not?
Yes,
Are
you are right.
Sadiq?
Yes, yes, doctor.
So x1 is less than 0 here. So this region is unfeasible. It doesn't satisfy this x1 is greater than 0. x2 is greater than 0. So this is x2. Here x2, here x2, sorry, here x2 equal to 0. It's the opposite. Here is x2 equal to 0. Here x2 is greater than 0. Here x2 lower than 0. So this is unfeasible solution or unfeasible region. This is feasible region. And this is for x1. You have here x1 positive and you have here x1 negative. So this is the feasible region here regarding this constraints. But this side is the feasible region regarding this constraints, x2 greater than 0. And if you have others, you may have different x1 square plus x2 square less than or equal whatever. You can have other constraints here. So these are this one constraint, and this is the feasible region. This is the other constraint. This is the other constraint, and this is the linear equality constraints like this one, the straight line. So you can, with these constraints, you can construct the feasible region. Okay, for this specific problem, if these constraints are not there, if the linear equality constraints is not there, and we have only the non-linear inequality constraints and x1, x2, all these regions are the feasible region. All this region will be the feasible region if this constraints is not there. But if you have this equality constraints, you have a straight line. So the part of the line that satisfy all other constraints, this is the feasible region here. So if you have greater than or less than, this is inequality constraints. If you have equal, this is equality constraints. I hope this addresses your question.
Yeah, it is clear, doctor. Thank you.
An optimal solution is a set of values of the variables that are contained in the feasible region and also provide the best value of the objective function in the category 1. So when you go to this example, all these points are feasible solutions. All these points in this part of the line are feasible solutions. So our task now is to find which point of this line will minimize your performance index or optimize, whether minimize or maximize. You need to search for the point on this line that gives you the minimum value or maximum value of your performance index or objective function. So this is our task after constructing the feasible region. In this case, an optimal solution is the set of values of the variables that are contained in the feasible region, yani feasible solution, and also provide the best value of the objective function in category 1, real performance index or the objective function. So this is the optimization problem, and usually the optimization problem formulation consists of as we mentioned, objective function, and subject to equality constraints h equal to 0, inequality constraints h is greater than or equal to 0, and you need to, our objective here is to find x. And here, find x that gives you the minimum value of the function, and at the same time satisfy these conditions, the equality and inequality. So x is the vector of the variables, could be, you have 2 variables, 3 variables, or for example, BI controller, you have KB and KI and the KD if you have BID controller. If you have lead lag controller, you have the gain KC, T1, and the T2, assuming that the structure of the controller is 1 over plus. This is lead lag structure. So you have here the controller parameters that needs to be optimized, KC, T1, T2. So these are the optimized parameters, X1, X2, X3. And if you have BID, also you have these optimized parameters. So h of x is the vector of equalities, and the g of x is the vector of inequalities. So this is the mathematical description of any optimization problem. طبعا minimize or maximize. Okay, and we will see how to convert from minimize to maximize later on. So this is the optimization problem in general, or typical formula or typical format of the optimization problem. So how to solve the optimization problem? We analyze the process in order to make a list of all variables. What are the optimized variables that is associated with your objective function that will affect your objective function? Okay, so you have to, of course, you are expert in your plant or your process or in your problem, and you know what are the variables that you are looking for to optimize. Determine the optimization criteria, the objective function, and specify the objective function. Okay, and then you develop the mathematical model of the process to define the equality and inequality constraints. Okay, do you have any question? Identify the independent and the dependent variables to obtain the number of degree of freedoms. Some variables are dependent, some of them are independent. You have to, classify your variables here. Apply a suitable optimization technique suitable to the problem, if it is linear programming or quadratic programming or nonlinear programming or any classical technique that you can implement, or even any evolutionary computational technique, and you can later apply. This is for optimization problems in general. So for any problem, you can implement any technique here. Check the results and examine its sensitivity to changes in the model parameters and assumptions. Of course, this is an extra step in order to see if you have any change in the optimized parameters, whether the performance will be satisfactory or it's very sensitive. Okay, so optimization problems can be classified the properties of fx, the objective function, هل هي single variable or multivariable. You have different optimized parameters, linear or non-linear. This f could be linear, could be nonlinear function, quadratic, could be linear function here for linear programming application, smooth or non-smooth. Smooth means the first derivative exists the first derivative of the function exists, non-smooth means the first derivative doesn't exist. And for example, for this function, it is continuous function, but it is non-smooth. And the derivative at this point here, the derivative on this side is, is different than the derivative on the other side. So the derivative at this point doesn't exist. So such function is non-smooth function. So this function, this characteristic is very important, of course, when you identify which technique is suitable for your problem. Properties of h of x and g of x, equality and inequality constraints, simple bounds, well, smooth or non-smooth also for these constraints, linear or non-linear constraints, and also no constraints if you have unconstrained problem. Maybe you have unconstrained problem. You need only to minimize or maximize f of x, whatever x is, and x is open, and there is no limitation, so no constraints. This is if no constraints, we call it unconstrained optimization, which is very simple, of course, to solve compared to constrained optimization. Properties of x, of the variable x, of the optimized parameter here. This optimized parameters could be time variant or time invariant. So we have a static optimization. If it is invariant, doesn't change with time. We have dynamic optimization of x of t, varying with time. Continuous or discrete. You may have this x continuous value, real value, can take any value, but sometimes in some optimization problems, the optimized parameter is discrete. It is not, maybe, مثلا, for example, integer number. And when you solve, for example, an optimization problem related to allocation of some of the equipment in your plant. So assume that this is the location 1, this is the location 2, this is the location 3, and this is the location 4, or cities, the traveling salesman problem, 5, and so on. So, and you need to find out what is the best location of installing some of the equipment here. I need to install this equipment in order to improve performance of the system. For example, minimize the losses or maximize, profit or whatever, and any objective function. So, which location? So, of course, in this case, you are searching for location, and these locations is either 1, 2, 3, 4, 5. So, in this case, your optimized parameter is just an integer number. So it is not continuous. You don't have 1.1 or 1.2. So in this case, you have a discrete optimized parameters. X here is discrete. Could be X take only integer values, as we mentioned here. And you can have mixed. In some problems, you can have mixed integer and also continuous variables. For example, you need here, you have, for example, you need to find the location and size of the equipment. Could be size, the size could be discrete. I hope you can mute yourself if you don't have any question. So please mute yourself. So in this problem, when you try to search for the location and also the location and size. In this case, you can have a size here as a discrete variable. You can have standard sizes. مثلا for the equipment مثلا يعني just for a motor مثلا, for example, you have 1 horsepower, you have 1.5 horsepower, you have 2 horsepower. You don't have يعني in between. So this is a discrete here. So you have you try to find out the location. So you have integer and also you have discrete, and probably you can also have some variables which, for example, continuous variables. يعني maybe مثلا if there is no restriction on the size, if you don't want to look at the existing, for example, sizes in the market, and the size is flexible, so you can make the size as continuous variables. So in some problems, you have mixed variables. Some of the variables are integer, some of them are discrete, some of them are continuous. So this is also could happen in optimization problems. So the problems or difficulties for the optimization, the objective functions and or constraints functions may have finite discontinuities in the continuous parameter values. And this is could create problems in classical optimization. And as you will see later on, when we have these evolutionary computation techniques, they are searching the space without considering whether the variables are or the functions are continuous or discrete or smooth or non-smooth, whatever the restriction there. Okay. So I'm still okay. The objective function and or the constraint functions may be non-linear functions of the variables. Also, this create if it is non-linear functions and you need to use linear programming, for example, you have to linearize these functions. So objective functions and or the constraints functions may exhibit nearly flat behavior for some ranges of the variables, or exponential behavior for other ranges. And you may have some kind of sensitivity in the functions there. This causes the problem to be insensitive or too sensitive. And if you have a very flat function as such, or very abrupt change in the function here, so any change in the parameter will affect much. So in this case, the function will be too sensitive. So the problem may exhibit many local optima, whereas the global optimum is sought. Of course, when we solve the optimization, we are looking for the global optimum solution. But sometimes you can have a function as such as we pointed out later or before, and we have some local optima here, local maxima, local minimum, local maxima, local minimum. So you have a multimodal function, and in this case, for some of the classical techniques, you can be trapped in this local minima. But you have here another solution, which is a global maxima, global minima within this range. This is the range you are searching in. Absence of feasible region. Sometimes it's very difficult, even to find the feasible region. In complex problems, to find the feasible region is a task by itself. It is not straightforward to find the feasible region to start optimization problem in some of the complex problems. So let us take the question of Khalid Sulaiman. Khalid Sulaiman.
Yes, Dr. Sam, and thank you. I can understand how a flat behavior can be too sensitive, but how could it be insensitive?
لا, this is insensitive. Here is insensitive. And the change in the parameter doesn't affect the function value.
Okay.
X1 here equal to 1, X1 here equal to 2. 1 and 2, they are giving you the same function value, right? But here, X equal to 3 and X equal to 3.1. So small change in the parameter gives you very high change in the function values.
Okay, I can see it now. Thank you.
Too sensitive now. Okay?
Yes, thank you.
Okay. So model reality differences. You can also, this is some of the difficulties. And you have a model, you optimize the parameters based on the model, and the models is little bit different than the reality due to some uncertainties, due to some approximation of nonlinearities, due to some imprecision in the modeling. You can have some differences. So even if you find out an optimal solution based on the model, when you go to the plant in real life and you set the values of KB and KI, maybe KB and KI based on the model will not give you the expected performance at the model in real life. So in this case, you have to do some kind of on-site tuning. We call it on-site tuning. And you get KB and KI, but when you go to the plant in real life, you have to do some fine-tuning of the KB and the KI. You start with those, and you start fine-tuning in order to have the satisfactory performance. Okay, the static optimization, plant design, sizing, and layout. The operation based steady state operating condition. So there is no time involved here. Parameter estimation, model fitting. You can see the parameters of the models, or you can create a model and you find the parameter model. It shows of the control parameters, gains, time constants to minimize a given performance index over short settling time, integral of error squared. All these we discussed just a few minutes back. Dynamic optimization, you need the track, some kind of tracking. So your determination of the control signal U of t, and this U is not fixed, U as a function of time, to transfer a dynamic system from an initial state to a desired final state. So you have some kind of tracking here, tracking the problems. So to satisfy the given performance index. The optimal plant start up and or shut down. So you have time involved here. Continuity of functions. How can you know whether the function given is continuous or discontinuous? How do you know?
Taking derivative.
Sorry?
The differentiation.
Differentiation
through the limits.
لا يعني طب let me ask you if this is the function. This function is continuous or non-continuous?
It's continuous.
It is continuous.
Yes, because every point in the region are connected to each other.
Exactly. Exactly. So the continuous, this is a continuous function. But smooth or non-smooth?
Not smooth.
This is non-smooth.
Not smooth.
Then if you go at this point, derivative here is positive, the derivative here is negative. So the derivative doesn't exist at this point. So this non-smooth, continuous, but non-smooth. Okay, so the function containing discontinuous or discontinuities can cause difficulties in solving optimization problems. This is in classical techniques. Yes, it could, it's non-smooth here for this one. If the system discontinuous means what? This is a discontinuous function here. You can have a function as such, and you have, this is very simple function. You can have function as such, and then you have here discontinuity in this region. Okay, so you can have discontinuity here, or you have here also discontinuous function here. So this is a these problems create these functions creates a problem in case of classical optimization. A function of a single variable x is continuous at a point x if the value of the function exists at x0 and the limit exists whether you have from both sides. You see, limit of f of x exists, okay, and the limit is existing. Approach x0 negative or x0 positive, you have the same value. If f(x) is continuous at every point in the region R, then f of x is said to be continuous through the range. Of course, you are searching for the range of x, and it is not only a certain value. But for this function is discontinuous, you can have here, it's clear, and you have discontinuity here. F of x is continuous, but derivative is doesn't exist at this value x, so this is non-smooth function here. So, do you have any question? Please, if you have, raise your hand. Unimodal and multimodal functions, and I hope these principles are, just to refresh your knowledge in optimization. When we discuss later on the evolutionary computation, we need to recall these principles from time to time. Thomas, do you have any question?
Sir, when you said if to find whether a function is smooth or non-smooth, we can find the derivative at a point. If does not exist, it is non-smooth. Just like that, to find continuity and discontinuity, do we have some mathematical method?
Yeah, but this is the mathematical method for the continuity. And in order to find or to check whether the function is continuous or not, the first at this point, at this specific point, it is exist. Okay.
Okay.
And when you have the limit of the f, whether from the x0 negative and x0 positive, the limits exist also, does exist, and also the same equal to the same value of the function at x0. So when you approach the function here, when you approach, this is x0, for example, when you approach x0 from this side, you approach to this value. And when you approach x0 from this side, you approach to this value, which is the same as a function of the value at x0. So if these conditions satisfied, in this case, you can say, this function is continuous at x0. Okay? Okay. Unimodal and multimodal functions And this is very important. And in classical optimization, if you have multimodal function, if you have several local minima and local maxima, in this case, you most likely, and it depends on the initial solution you start with, you can be trapped in local minima or local maxima. So a unimodal function, the range of specified for x has a single extremum value, minimum or maximum. Now, for example, you have this function, for example. This function is unimodal. You have only one of the optimal solution here if you need to minimize. For this example, this is the unimodal. You have only one point, which is the extremum point, and this extremum point is a maximum or maximum point. And sometimes you have the function as a multimodal function. You have several extrema points, and if f prime or differential or derivative of the matrix equal to derivative of the function equal to 0 at the extreme point, the point is called stationary point, and this stationary point could be stationary point. Let us say we call it saddle point, and could be maximum point, could be minimum point. The derivative of the function here is 0. The derivative of the function here is 0. For the multimodal, you can have a lot of these optimal and maximum point. You may have also some of the saddle point here, where the derivative equal to 0, but the it is not a local minima or local maxima. So this is a multimodal. So these points are called stationary, and this is a stationary point, derivative equal to 0. This is a stationary point. This is a stationary point, derivative equal to 0. This is a reflection point. We call it reflection point. This is also derivative here equal to 0, derivative equal to 0. All these points are stationary points. There is a distinction between the global extremum, or the biggest or smallest, between the a set of extrema, and the local extrema or any extrema. But of course, as you can see here, this point is a global maximum. This is local maximum. This is local maximum. We have only one global here. For the minimum, probably this point is the minimum point in the function within this range, of course. Within this range, this is the minimum value. So this is called global within this range. And this value is a local minima. Sharif Ibrahim, please. You have a question?
Doctor, where is the location of the saddle point from this graph?
This is called the reflection point. Or saddle point. This is a saddle point also. So the function behaves as like here, flat point.
I can see the pointer. I can see the pointer. Where is actually your pointer? Or yeah. Okay.
And this point here, you can see it, and like let us say this, مثلا, if you have, for example, this function, this point, derivative equal to 0, but it is not local maxima or local minima. It is just a reflection point. We call it reflection point. Okay? And here we define the stationary points. What are the stationary points? The definition of the stationary point is if derivative equal to 0. Okay? So a derivative equal to 0 means a stationary point. And this stationary point could be local maxima could be local minima, could be reflection point. Okay? What will differentiate between these two possibilities? What do you think? How can we differentiate between maxima, minima, and the reflection point? Salim Ghanem?
It should be the second derivative.
Exactly, second derivative. You have to get f double prime. If f double prime is greater than 0, but this is what? This is minimum.
Minimum.
If it is greater than, if it's less than 0, يبقى maximum. If it is equal to 0, يبقى reflection point. This is the point. And what differentiates between these two possibilities is to find out the second derivative of the function in order to have this. This is, of course, the basics in calculus. When you want to get the maximum value or the minimum value, you get the first derivative equal to 0, and then the second derivative, and if it is greater than 0, then this is a minimum or minimum, greater or minimum, yani, with these possibilities that we have discussed here. Okay. Note, many numerical procedures terminate at a local extrema. Yani, most of the, لأنك أنت if you have any iterative technique, and for example, for this function here, if you start with x0, for example, here, this is x0, and you need the initial guess. If this is the initial guess, and you need to minimize, so you will end up with this point. So you have here, this is a global. You are lucky. You are lucky انك انت to reach to the global. But if you start randomly here, so you end up with this one, which is the local optima. You will be trapped here, and you say, this is the optimal solution. But actually, this is not the optimal solution, or this is not the global optimal solution. The global optimal solution is here. So it is sensitive to the initial. Usually, the iterative techniques or gradient-based techniques are sensitive to the initial guess or initial solution. And such limitation in classical techniques such limitations is avoided in evolutionary computation. So whatever the initial solutions, then you are handling a population of solutions, and in this case, you can have better searching capability. Salim Ghanem, time is over, I know.
Yeah, regarding this limitation of initial guess, is there a technique or a shortcut to start with initial guess that will lead us to the best result?
Of course, if you are familiar with your plant or your model or you can usually start with the wise initial guess. يعني for example, انت طبعا الباك جراوند بتاعتك باور. Usually when you solve the load flow problem in power systems, you start with the مثلا flat voltage. All the voltage is equal to 1. So this is a good start. لأنه usually the voltage usually is يعني within or around 1. So you can start with 1. So, but this is based on your experience, based on your knowledge about your plant. So if you have such knowledge, you can select the good optimal solution, good initial solution in order to reach to this. But if you don't have the nature of the problem, if you don't have the, for example, the search space, So in this case, you are start randomly, and of course you need to run it several times, changing the the initial solutions every time, and see. Sometimes you have, for example, diverge. You can diverge. If this is the case, you can have, for example, if you need to, for example, sometimes you can, the technique can diverge rather than converge to this. And it can lead you to, for example, if you start somewhere here, and then you search for the minimal solution, so it leads you to to nowhere. Is it clear?
Yeah. Okay. Thanks.
And actually, I was preparing a quiz for today, which is like 3 minutes quiz, multiple choice in Blackboard, but unfortunately there is no time for today to take it. But usually this would be the scenario, and maybe every week or every class, I don't know, depends on the material. I will give you like very simple multiple choice quiz. I mean, weight is very, weight, but weight is very low, but it will accumulate. Maybe if you have, for each class, you have very quick quiz, so this will accumulate later on. So this will be the approach, but maybe from starting the next class, inshallah. Okay. Do you have any question? If you have any question, please stay with us. Otherwise, you can leave the meeting. Okay. I will stop recording.
Sorry, doctor, I wanted to